pace of AI innovation right now is absolutely breathtaking, isn't it?
Oh, completely. New models, new applications. It feels like every single day.
Yeah, but here's the thing. Uh, it's one thing to use a high-level API for some pre-trained model and feel like you're, playing with AI.
Right.
It's an entirely different beast to truly master the foundational expertise,
Mm-hmm.
the stuff you need to become a creator of AI,
Mm-hmm.
to build those robust, scalable, and, well, reliable systems that actually run things.
Exactly. And that's what this is about.
So this deep dive is your shortcut to understanding that foundational knowledge, kind of cutting through the noise to the core insights.
Precisely. Today, we're going to unpack the roadmap to deep expertise in three key pillars of modern AI: computer vision, deep learning, and multimodal AI.
Okay.
We'll start with how machines actually see the visual world. It's maybe simpler than you think. Then we'll dive into the powerful learning engines that enable this.
Right, the deep learning part.
Yep. From there, we'll explore how different senses, quote unquote, are combined in multimodal AI.
I did the practical bit.
And then we bring it all to life. We'll blueprint and build a real-world production-ready system. This isn't just theory. It's about getting your hands dirty, building end-to-end applications.
Okay, let's unpack this first part then.
Ah.
How do computers, these machines that fundamentally deal in numbers, manage to see the world around them? I mean, they don't have eyes like we do, right?
Yeah.
So what's their secret?
That's a great starting point because it is counterintuitive. For a computer, you see, an image isn't a picture in the way we think of it.
But
It's just a vast grid of numbers. Think of it like a huge spreadsheet.
a spreadsheet.
Yeah.
Yeah.
Every tiny dot, every pixel has a numerical recipe for its color, basically, how much red, green, and blue light intensity it has. Values usually between 0 and 255.
So RGB values for every single pixel.
Exactly. So a standard high-definition image, say 1920 by 1080 pixels, that's over 2 million pixels.
Huh.
And each has 3 color values. So you're looking at over 6 million numbers just for one single image.
6 million numbers. Wow. That sounds like an overwhelming amount of data to process.
It is?
So what's image processing then? Is that like giving the computer special glasses or something?
Huh. You could sort of say that. Image processing is precisely the set of techniques we use to get that raw numerical data ready for analysis.
Oh, okay.
It's about transforming, enhancing, maybe normalizing those numbers to make them easier for the AI to understand.
Like adjusting contrast or removing noise.
Exactly. Adjusting contrast, reducing noise, scaling values into a consistent range. It's the pre-processing step, really. It ensures the vision models get the cleanest, most useful input possible.
That makes sense. So once a computer sees an image as this numerical data, what's the first thing we teach you to do with that information? What kinds of visual puzzles can they solve?
Right. Once it can interpret the numbers, we can ask it to solve a whole hierarchy of problems, each one building on the last. The simplest is probably image classification.
Classification. Just saying what it is.
Exactly. Assigning a label to the entire image. Think of it as asking, what is in this image? It could be binary classification, simple cat or not a cat.
Okay.
Or multi-class, where it picks one label from many mutually exclusive options, say dog, car, or tree.
Mutually exclusive, right.
And sometimes an image can have multiple things going on, like a person, a dog, and a park, all at once. That's multi-label classification. They aren't exclusive.
Okay, so classification tells us what the image is generally about. What's the next step up?
The next step up is localization and detection. This moves beyond just what to where things are in the image.
Yeah, finding the things.
Yeah. With simple localization, you might identify one main object, say a car, and draw a bounding box around it. That box is defined by 4 numbers, center coordinates, width, height.
Just one box.
For simple localization, yes. But for a real-world scene, you often have multiple objects. And that's where object detection comes in.
Okay, like identifying all the cars and people.
Precisely. Think of the famous YOLO model. You've probably seen demos of it tracking multiple cars, pedestrians, traffic lights in live video.
Yeah, those are impressive. How does it work?
Well, a common approach, like in YOLO, is to divide the image into a grid and then predict for each grid cell whether an object center is in it, what the object is, and its bounding box dimensions.
So if detection gives us a rough box, what if we need to know the exact shape of something? Like tracing its outline perfectly.
Now you're talking about segmentation. This takes us to the most granular level, pixel-level understanding.
Every single pixel.
Every single pixel. Semantic segmentation gives every pixel in an image a class label, like road, sky, or car. But crucially, it doesn't distinguish between individual cars. All pixels belonging to any car are just labeled car.
Okay, so all cars are just one category.
Right. If you need to know this is car number 1 and that's car number 2, you need instance segmentation. It detects each individual object instance and gives it its own unique pixel-perfect mask or outline.
That sounds much more useful for counting things or tracking individual objects.
It is. And then for the, let's say, ultimate visual understanding, there's panoptic segmentation.
Panoptic.
Yeah, it's the most comprehensive. Imagine knowing not just that there's a car, but knowing its exact pixel-perfect outline and distinguishing it from other cars, and also knowing the exact outline of the road and the sky. It understands everything in the image, assigning both a semantic class and an instance ID to every single pixel. It handles both things, countable objects like cars and people and stuff, amorphous regions like sky, grass, or road.
Wow. Okay, that all sounds incredibly precise and powerful with today's AI. But how on earth did we do this kind of stuff before the deep learning revolution? It feels like magic now, but what was the old way?
Oh, it was far from magic, let me tell you, and often very, very labor-intensive. Before deep learning, engineers had to painstakingly handcraft what we call feature extractors.
Handcraft. You mean manually code them?
Exactly. They manually wrote code to look for specific, predefined patterns in the image data. For example, they design algorithms to find sharp changes in pixel intensity, which usually signal an edge. Or they'd look for particular corner shapes.
So they were essentially trying to hard code what an edge looks like or what a corner looks like for the computer.
Precisely. They develop things like canny edge detectors or Harris corner detectors, or more complex feature descriptors like SIFT, SRF, or HOG. These aim to create robust numerical descriptions of specific visual patterns, trying to make them resistant to changes in lighting or viewpoint.
I remember HOG, histogram of oriented gradients.
Yep, that's a classic.
Yeah, okay.
It was incredibly clever engineering for its time. But the key thing is the intelligence was always in our human design of those features. Once these predefined features were extracted,
You'd feed them into a regular machine learning model.
exactly. You'd feed these feature vectors into traditional ML models like support vector machines, SVMs, or random forests for the final classification or detection task.
What's fascinating here is how limited that approach really was looking back. I remember spending weeks, maybe months, trying to perfect an edge detector for a specific type of industrial image.
Oh, yeah.
And it was incredibly frustrating because if the lighting changed just slightly or the angle was a bit off, the whole thing just fell apart.
That's exactly it. The classical approach was inherently brittle. It required immense domain expertise to design effective features for a specific problem.
Right.
And the models didn't generalize well to new, unseen conditions because the intelligence was fundamentally bottlenecked by those fixed human-designed features.
So it couldn't adapt.
Nope. And that rigidness, that brittleness, really paved the way for a fundamental philosophical shift in AI. We moved away from a model-centric world where human ingenuity and algorithm design was king, towards a data-centric one. The idea became, let the data teach the model what features are actually important, rather than us trying to guess and hard-code them.
And this is where it gets really interesting, right? How did deep learning just shatter those limitations and automate this incredibly complex feature engineering? How did it enable that shift to a data-centric world where the computer learns to see for itself?
Well, the answer for, over a decade now has largely been convolutional neural networks, or CNNs.
CNNs, okay, I've heard that term a lot.
Yeah, their design is actually loosely inspired by the animal visual cortex, how our brains process vision. And they've been incredibly effective at capturing the spatial hierarchies of features in an image.
How do they work, basically?
Okay, at their core are these things called convolutional layers. Think of these as small, trainable magnifying glasses or filters.
Filters?
Yeah, they contain learnable filters, tiny patterns of numbers, also called kernels. These filters don't just sit still, they slide or convolve across the entire input image section by section.
Sliding across, what does that do?
As they slide, they perform a mathematical operation, a convolution that checks if the specific pattern the filter represents, like a vertical edge or a specific texture or a curve, is present in that part of the image. If the pattern is there, the filter activates strongly.
So these filters are literally learning what patterns to look for. They're like developing their own internal edge detector or texture finder automatically.
Exactly. The filter weights the numbers inside them are learned during the training process using backpropagation and gradient descent. This means different filters automatically specialize in detecting specific low-level features. You also need to consider things like stride, how many pixels the filter jumps each time, and padding, adding borders around the image to control the output size.
Okay, so convolutional layers find basic patterns. What else is in a CNN?
After these convolutional layers, you typically have pooling layers. The most common type is max pooling.
Explain.
Yeah, it basically takes a small region of the feature map produced by the convolutional layer and just outputs the maximum value from that region. It effectively downsamples the representation.
Why do that? Shrink the data.
Partly, yes. It reduces the amount of computation needed in later layers, but it also helps make the learned features more robust to small shifts or distortions in the input image. We call this local translation invariance. So if an object moves slightly left or right, the network is more likely to still recognize it.
Makes sense. And then at the end.
Finally, after several layers of convolution and pooling have extracted increasingly complex features, these rich feature maps are typically flattened into a long 1D vector. This vector is then fed into standard fully connected layers, like you'd see in a basic neural network, for the final classification or prediction task.
What's truly mind-bending about CNNs isn't just that they learn features, it's that they discover an optimal hierarchy of features all on their own.
Exactly.
Going from simple patterns like edges and corners in the early layers to more complex features like object parts in the middle layers, and eventually recognizing entire objects in the deeper layers, all without being explicitly told.
That automatic, data-driven discovery of hierarchical representation is precisely what replaced all that manual feature engineering work. It was a monumental leap.
If we connect this to the bigger picture, though, just when we thought CNNs were the undisputed kings of computer vision, something else came along, right? Something adapted from a totally different field.
That's right. A completely new paradigm emerged, adapted, perhaps surprisingly, from the world of natural language processing, NLP.
NLP, like text processing.
Yep. The groundbreaking 2017 paper, Attention is All You Need, introduced the transformer architecture primarily for language tasks like translation. But its core mechanism, this thing called self-attention, proved so incredibly powerful in general that researchers thought, hey, maybe we can adapt this for vision. And that led to the Vision Transformer, or ViT.
Vision Transformer, ViT.
Yeah. And the ViT marks a radical departure from how CNNs work. Instead of using those local filters sliding across pixels, it treats an image more like a sentence made of words.
How does an image become a sentence? That sounds pretty wild.
It's quite clever, actually. The first step is to break the image down into small, fixed-size, non-overlapping image patches. Imagine chopping the image up into a grid of little squares, like postage stamps.
Okay, got it. Little squares.
Each of these squares is then flattened out into a long 1D vector of pixel values.
Flattened, right.
Then each of these flattened patch vectors gets projected into a higher dimensional space, creating what's called a patch embedding. It's a learnable numerical representation for that patch.
So each patch gets its own vector code.
Exactly. And this next part is crucial. Because we just chopped up the image and treated the patches like a sequence, we lost all the information about where each patch originally was in the image.
Ah, the spatial information.
Right. So a learnable positional encoding vector is added to each patch embedding. This reintroduces that vital spatial information, essentially telling the model, this patch came from the top left corner, or that one was from the middle right.
Okay, that makes sense. You need to know where things are. So now we have a sequence of these patch embeddings, each tagged with its location. What happens then?
That sequence of embedded patches then enters the standard transformer encoder block, the same kind used in NLP.
The transformer core.
Yep. And the absolute core magic here is the multi-head self-attention MSA mechanism.
Self-attention. That's the key part from the paper title.
That's the one. This is where each patch embedding dynamically interacts with every other patch embedding in the sequence. It calculates attention scores to weigh how relevant each patch is to every other patch.
Wait, every patch talks to every other patch simultaneously?
Basically, yes. Think of it like every postage stamp in the image looking at every other postage stamp at the same time, figuring out how they all relate to each other no matter how far apart they are.
Wow, that's completely different from CNNs focusing on local areas.
Totally different. This allows the ViT to model global relationships and long-range dependencies across the entire image right from the very first layer. CNNs have to build up that global understanding gradually through successive layers of local operations. The transformer encoder also includes standard feed-forward networks,
Yeah.
FFN, after the attention layers.
Okay, global context from the start. How does it make a final decision, like classification?
For classification tasks, a common technique is to add an extra learnable classification token to the beginning of the sequence of patch embeddings. The special token goes through the transformer layers along with the patches, and its final output embedding is then fed into a small classifier head, usually a simple linear layer, to make the final prediction for the whole image. It kind of aggregates the relevant information from all the patches.
So we have CNNs, these hierarchical pattern detectors with built-in spatial biases, and ViTs, these global relationship reasoners that learn almost everything from data. As a developer, maybe someone building an application, what does this all mean? How do you choose between these two powerful architectures? What are the practical trade-offs?
That's a critical question because they really do have distinct strengths and weaknesses.
Huh.
Let's compare them head-to-head on a few key aspects.
Yeah.
First, let's talk about inductive bias. This is basically the set of assumptions an architecture makes about the data.
Assumptions.
Yeah. CNNs have strong built-in assumptions or biases about how images work. Things like locality, nearby pixels are more related than distant ones, and translation invariance. A pattern like a cat's ear is still a cat's ear, whether it's top left or bottom right. These biases are baked into the convolutional and pooling operations.
Right, those seem like pretty good assumptions for images. What about VTs?
ViTs, on the other hand, have a much weaker inductive bias regarding spatial structure. They make fewer assumptions. The self-intention mechanism treats all patches as potentially related, regardless of distance. They have to learn almost all the spatial relationships directly from the data itself.
So what does that mean for how much data they need to learn effectively? Does the bias help CNNs?
It absolutely does. It leads directly to major differences in data efficiency. Because CNNs have these helpful built-in priors, they are generally very data efficient. They can learn effectively even on smaller to medium-sized data sets.
And VITs needing to learn everything.
They are the opposite. VITs are quite data hungry. They typically need absolutely massive pre-training data sets. We're talking hundreds of millions, even billions of images to truly learn those fundamental visual patterns from scratch and start outperforming well-tuned CNNs. Without that scale, their lack of bias can be a disadvantage.
Wow, hundreds of millions. That impacts scalability, I guess.
Definitely. It impacts scalability in both directions. CNN performance tends to plateau eventually as you add more data or make the model bigger. VITs, however, seem to scale exceptionally well. The more data and compute you throw at them, the better they generally get. This makes them ideal for creating those enormous foundation models we hear so much about.
Okay, what about the cost to run them? Computational cost.
CNNs are generally more computationally efficient, especially on hardware optimized for convolutions, because their operations are local. VITs, especially the self-attention part, can be quite computationally expensive. That mechanism where every patch attends to every other patch has a cost that grows quadratically with the number of patches, which can be a bottleneck for very high-resolution images or long sequences.
Quadratic cost, right? So pulling it all together, what are the typical use cases? When would you reach for a CNN versus a VIT today?
Well, CNNs are still excellent and widely used for many general computer vision tasks. They're often the go-to choice when you have limited data or when you need to deploy on resource-constrained environments like edge devices or mobile phones due to their efficiency.
Okay. And VITs?
VITs really shine when you're aiming for state-of-the-art performance on large-scale academic benchmarks, or when you're building or using large foundation models that have been pre-trained on massive data sets. They form the vision backbone of many cutting-edge multimodal models today.
So it really reinforces that tension we talked about earlier.
Yeah.
Human knowledge and assumptions baked into an architecture like a CNN versus these more general methods like VITs that learn almost everything from data, provided you have enough of it and enough compute.
Exactly. And the trend, certainly in large-scale research, shows that massive computation and data often, though not always, win out in the end.
But just to clarify for maybe a smaller startup or a researcher without access to Google-level resources, is there still a really strong case for CNNs in those more practical, maybe less state-of-the-art chasing scenarios?
Oh, absolutely. That's a vital practical consideration. For many real-world applications, especially if you're working with proprietary datasets that aren't web scale or deploying on edge devices where efficiency is paramount, CNNs often hold a significant advantage.
Because they're more data efficient and computationally cheaper?
Precisely. They're often faster to train, easier to fine-tune on smaller datasets, and require less computational power for inference. So yes, while ViTs are pushing the absolute limits on benchmarks and powering huge foundation models, CNNs remain incredibly relevant, powerful, and often the more practical choice for a vast array of problems you encounter day to day.
That makes perfect sense. It's good to keep that perspective. Okay, this raises another really important question, though. As these models, whether CNNs or ViTs, become these incredible black boxes that automatically learn such complex features and relationships, how do we understand why they make particular decisions? Are we just trusting them blindly?
That's a huge area of research and concern interpretability or explainable AI, XAI. And no, we're not just trusting them blindly, or at least we shouldn't be. There are various techniques emerging to help us peer inside these black boxes.
Like what? Can we actually see what they're thinking?
Well, thinking might be strong, but we can get glimpses. One fascinating method is feature visualization. The idea is you take a specific neuron, say, deep inside the network. Then you start with a random noise image and use optimization techniques to gradually change that image to make that specific neuron fire as strongly as possible.
So you're finding the neuron's ideal input.
Exactly. You're asking, what does this neuron like to see? And what you often find is that neurons in early layers respond most strongly to simple things, like oriented edges or specific color gradients. Neurons in deeper layers might respond to more complex textures, object parts, or even entire object categories, like a dog's face or a wheel. It directly visualizes what kinds of features the network has learned to detect at different levels.
So we can literally see these learned patterns. That's pretty wild.
It really is. Then there's attribution, or saliency mapping. While feature visualization shows what a neuron could respond to in general, attribution techniques try to explain a specific prediction for a specific input image.
How does that work?
Methods like saliency maps or GradCam essentially calculate how sensitive the final output prediction, like the dog score, is to each pixel in the input image. The result is often shown as a heat map overlaid on the original image, highlighting the pixels that were most influential in reaching that particular decision. So if the model classifies an image as dog, the heat map should light up the pixels actually corresponding to the dog in that picture.
Ah, so it shows you where the model was looking, so to speak, for that specific decision.
Exactly. It helps answer, why did you classify this image as a dog? And for an even more advanced concept, researchers are exploring circuits. This involves trying to trace the connections and pathways within the network to understand how specific computations or concepts are implemented.
It's like how simpler features combine to form complex ones.
Precisely. For example, trying to identify a subnetwork or circuit responsible for detecting circles and seeing how it might be composed of lower-level circuits that detect curves, which in turn are built from circuits detecting edges. It's like trying to reverse engineer the network's internal algorithms. It's still early days for circuits, but it's a really promising direction for deeper understanding.
Okay, so we've gone from pixels to complex vision models. Now, humans, we don't just see. We integrate sight, sound, language seamlessly to understand our environment. What happens when we try to teach AI to do the same, moving beyond just vision into something much richer?
This is truly the frontier, or at least a major one. Multi-modal AI. These are systems designed specifically to process, relate, and sometimes generate information from two or more different types of data, different modalities simultaneously.
Modalities
Like images and text, or video and audio, or maybe even combining visual data with structured data from a database, or sensor readings like temperature or depth information from LiDAR.
I can immediately see the power there. You mentioned self-driving cars earlier. They absolutely need to combine camera vision, which gives texture and color, with LiDAR, which gives precise depth and distance measurements.
Exactly. Or think about healthcare. An AI system might need to analyze both a visual X-ray image and the accompanying textual radiologist's report to make a more accurate diagnosis.
So it's about getting a more complete, more holistic picture by combining different kinds of information.
Precisely. Different data types often provide complementary information. What one modality lacks, another might provide. By integrating these different streams, a multimodal AI can potentially achieve a far more robust, nuanced, and human-like understanding than any system relying on just a single modality could ever achieve on its own.
What's fascinating here is how we actually combine these different senses or data streams. Is there one standard way to fuse them together inside the AI?
It's definitely more of an art and an active area of research than a single settled method, but generally we talk about three primary strategies for this fusion process.
Okay, what are they?
The first is early fusion. sometimes called input level or data level fusion. Here, features or even raw data from different modalities are combined right at the very beginning of the pipeline before they go into the main processing model.
Like just sticking them together.
Pretty much. Imagine taking the raw pixel values from an image and maybe the word embeddings from a text description and just concatenating them into one big input vector before feeding them into a single large neural network.
Okay, so smashing them together right from the start. What's the opposite end of the spectrum?
The opposite is late fusion, often called decision-level fusion. This strategy involves training separate, independent models for each modality first. So you might have a dedicated vision model and a dedicated text model.
Trained completely separately.
Initially, yes. Then their final outputs or predictions are combined only at the very end. For example, you might average the probability scores they produce or use some kind of voting mechanism to make the final multimodal decision.
That seems simpler in some ways.
It can be simpler to implement initially. And then the most common approach, especially in modern complex architectures, is somewhere in the middle. Intermediate fusion, sometimes called hybrid fusion or feature-level fusion.
How did that work?
Here, each modality is first processed by its own specialized encoder, maybe a CNN or ViT for images, and a transformer for text. These encoders produce high-level feature representations for each modality.
Okay, so rich feature vectors for image and text.
Exactly. Then, these high-level features are fused together within the hidden layers of the model. This fusion often uses sophisticated mechanisms like cross-attention.
Cross-attention, like the self-attention and transformers.
Similar idea, but instead of a modality attending to itself, features from one modality can attend to and query features from the other modality. So the text features can look at the image features to find relevant visual information and vice versa. This allows for much richer interaction between the modalities before the final prediction is made.
For years, it felt like the Holy Grail was just making computers see, effectively, maybe with CNNs. But then it feels like a truly groundbreaking idea came along that started to really blur the lines between seeing and understanding language. One specific model really changed the game here, didn't it?
It absolutely did. You're almost certainly thinking of OpenAI's CLI model.
CLIP, yes. Contrastive Language Image Pre-training.
That's the one. Its architecture, when you look at it, is surprisingly elegant and simple. It uses two separate encoders. One is an image encoder, typically a ViT or a ResNet-based CNN, which takes an image and outputs a single feature vector, an embedding.
An image embedding.
Right. And the other is a text encoder, usually a standard transformer, which takes a text string, like a sentence or caption, and also outputs a feature vector, a text embedding, designed to be in the same dimensional space as the image embedding.
So it's learning to represent both images and text in the same shared language or vector space. They can be compared directly.
Exactly. That's the goal. And the real genius of CLP lies in how it learns this shared space through its contrastive pre-training objective and the sheer scale of data it used.
Contrastive, meaning it learns by comparing things.
Precisely. Instead of relying on expensive, manually labeled data sets like this image contains a cat, a dog, a park, CLIP was trained on a massive data set of 400 million image-text pairs scraped directly from the internet. Just images and their associated alt text or captions.
400 million, that's huge. And noisy, I bet.
Huge and definitely noisy, weakly supervised data. The training objective is simple but powerful. For a given batch of image-text pairs, the model learns to maximize the similarity, usually cosine similarity, between the embeddings of the correct matching image and text pairs.
Okay, pull the right pairs closer together in the embedding space.
Right. And simultaneously, it learns to minimize the similarity between the embeddings of all the incorrect pairings within that batch. The image with all the wrong captions and the caption with all the wrong images.
Push the wrong pairs further apart.
Exactly. This contrastive loss powerfully forces the model to learn which visual features correspond to which textual concepts, effectively learning a shared semantic space by leveraging this vast, noisy, but freely available web data.
What's really astonishing about CLP, I think, is that by simply learning to contrast images with their raw text descriptions at that scale, it seemed to develop a fundamental, almost common sense understanding of visual concepts. Not just recognizing a cat, but understanding the essence of catness across different styles and contexts.
That's a great way to put it. It learned a surprisingly robust visual representation.
And this allowed it to do something pretty magical. Classify images into any category, even ones it had never explicitly been trained on, without needing any retraining. This zero-shot power felt like a monumental leap beyond previous models.
That's absolutely right. A traditional image classifier is trained on a fixed set of categories, maybe 1,000 object classes in ImageNet. If you wanted to classify a new object, you have to retrain or fine-tune it. With CLP, because it understands the relationship between images and arbitrary text, you can perform zero-shot classification for any new categories on the fly. You just create descriptive text prompts for your target classes, like a photo of a car, a drawing of a dog, a watercolor painting of a landscape.
So you just write down what you're looking for.
Yep. You get the text embeddings for these prompts using CLIP's text encoder. Then you take your input image, get its image embedding using CLIP's image encoder, and simply compare the image embedding to each of your text prompt embeddings using cosine similarity.
And the text prompt whose embedding is closest to the image embedding is your predicted class.
Exactly. The prompt with the highest similarity wins. This incredible flexibility classifying anything described by text without retraining has made CLIP a fundamental building block in countless downstream applications, from image retrieval to guiding generative models.
Indeed, this whole concept of learning powerful representations from noisy web-scale data, especially using contrastive methods like CLIP, didn't just enable better understanding and classification, it really cracked open another huge frontier, actually creating entirely new content.
Yes, this takes us squarely into the generative frontier of multimodal AI. We started seeing this first with models capable of creating new visual content. Perhaps the earliest widely known were GANs, or generative adversarial networks.
GANs, right? The ones with the two competing networks.
That's them. You have two neural networks, a generator and a discriminator, locked in this adversarial game, a sort of digital cat and mouse. The generator takes random noise as input and tries to transform it into realistic-looking images or other data. The discriminator's job is to look at both real images from the training set and fake images from the generator and try to tell them apart.
So the generator tries to fool the discriminator.
Exactly. As the discriminator gets better at spotting fakes, it provides feedback to the generator, pushing the generator to produce even more realistic images to fool it. This constant competition drives both networks to improve, resulting in often stunningly realistic generated images.
I remember seeing those GANs for things like generating fake celebrity faces. They were incredibly realistic, sometimes unsettlingly so. But GANs can be tricky to train, right? What's the cutting edge now for high-quality image creation?
GANs can indeed be unstable and difficult to train well. The current state of the art for generating really high-fidelity, diverse images are generally considered to be diffusion models.
Diffusion models, okay, how do they work? It sounds less
Yeah.
adversarial.
It is less adversarial. Their process is almost magical in its conceptual simplicity, though the math can get involved. It works in two stages. First, there's a fixed forward diffusion process. Imagine you start with a real training image. You progressively add a tiny amount of Gaussian noise to it over many, many small steps, maybe hundreds or thousands. Eventually, after enough steps, the original image is completely transformed into pure random noise, like static on an old TV.
Okay, so you destroy the image with noise systematically. Why?
Because then you train a neural network, usually a UNet architecture, to learn the reverse process. This network is trained to predict the noise that was added at each step, given the noisy image at that step. Essentially, it learns how to undo the noising process, how to take a slightly noisy image and make it slightly cleaner.
Ah, so it learns to denoise, step by tiny step.
Precisely. Now, here's the cool part. To generate a completely new image, you start with pure random noise, just static. Then you apply that learned reverse denoising process iteratively. At each step, the network predicts the noise in the current image and subtracts it, gradually refining the random static into a coherent, realistic-looking image that resembles the data it was trained on.
So it's like teaching an AI to sculpt a detailed image out of a block of pure noise by repeatedly removing the unnecessary noise.
That's a great analogy. And the real trick for text-to-image models, which we'll get into more, is that a text embedding derived from your prompt is used to guide this denoising process at each step, steering the generation towards an image that matches your textual description.
Fascinating. Are there other important generative approaches?
Yes, another important category, especially for tasks involving both vision and language generation, are large autoaggressive models, which are heavily inspired by the success of large language models, LLMs, like GPT. Models like Google's Flamingo essentially combine a powerful pre-trained vision encoder to understand the image with a pre-trained LLM to handle language and reasoning. They use clever techniques like a perceiver resampler to inject visual information into the language model, allowing it to process interleaved image and text inputs and perform tasks like visual question answering or image captioning with impressive few-shot learning capabilities.
Okay, so we have CLAP for understanding, GANs and diffusion models for generation, and these large autoregressive models blending vision and language. For listeners looking to dive deeper into this rapidly evolving multimodal world, what are some of the most influential, maybe foundational models out there that have really shaped the landscape recently?
Sure, beyond CLIP, which is fundamental for its zero-shot capabilities and as a component in many other systems you should definitely know about. Flamingo from DeepMind Google, which we just mentioned, known for its impressive few-shot learning on VQA and captioning by integrating vision with LLMs, stable diffusion from Stability AI and collaborators, perhaps the most well-known open-source text-to-image diffusion model, which made high-fidelity image synthesis widely accessible. Lava, large language and vision assistant, an excellent open source project demonstrating how to effectively connect a vision encoder, like CLIPs, to an LLM, like Llama, to create capable instruction-following vision language models. And looking towards video, OpenAI Sora is pushing the boundaries of text-to-video generation, focusing on high-fidelity, longer duration, and temporally consistent video synthesis, though it's not yet widely released.
That's a great list. It really shows the progression towards richer interactions. Okay, now that we understand the building blocks, how machines see, the deep learning architectures, fusing modalities, these key models, it's time for the rubber to really hit the road. How are these individual components actually combined to create sophisticated, almost human-like interactions with visual information?
Right. This is where the true power of combining these pieces comes into play, moving from just passive understanding to active interaction. A classic example is visual question answering, or VQA.
VQA, we touched on that, answering questions about pictures.
Exactly. The goal is pretty intuitive. You give the system an image and an open-ended natural language question about that image, and it should provide a natural language answer. This isn't just simple object recognition. It requires the model to deeply understand the language of the question, identify relevant visual concepts in the image, and often reason about the relationships between them.
So it's not just, is there a dog, but maybe, what color is the collar on the dog sitting under the tree?
Precisely. It requires that compositional understanding. A typical, let's say, canonical VQA system follows a multi-stage pipeline. First, image feature extraction. A pre-trained vision model, like a CNN or ViT, processes the image and usually outputs a set of localized feature vectors representing different regions or objects in the image.
So features for different parts of the image.
Yep. In parallel, question encoding takes place. A text encoder, like an LSTM, GRU, or transformer, processes the natural language question and produces a vector representation capturing its semantic meaning.
Got the image features, got the question meaning. Then fusion.
Then comes the critical multimodal fusion, often involving attention mechanisms. Here, the encoded question representation is used to query the image features. The model learns to dynamically attend to or focus on the most relevant parts of the image needed to answer that specific question.
So for what color is the hydrant? The attention mechanism learns to kind of highlight or focus on the hydrant region in the image features.
Exactly. It figures out which visual information is pertinent to the query. Finally, this fused representation, which now combines information from both the relevant image parts and the question, is fed into an answer generation module. This might be a simple classifier predicting from a fixed set of answers, or increasingly, a decoder that generates a free-form natural language answer.
And these systems need data to learn, right?
Oh yes, lots of it. They're typically trained on large-scale data sets specifically designed for VQA, like the popular V2 dataset, GQA, which focuses more on compositional reasoning and spatial relationships, or SciLV, a diagnostic dataset using synthetically rendered 3D scenes to test specific reasoning abilities like counting, comparing attributes, and understanding spatial relations in a very controlled way.
This naturally raises the complementary question. If we can ask detailed questions about images, can we also go the other way and create detailed images just from words?
Absolutely, and that brings us back to text-to-image synthesis, particularly with the powerful diffusion models we discussed earlier. This is the capability that has really captured the public imagination recently, with models like Stable Diffusion, Midjourney, and Daily 2.
Right, typing in a sentence and getting a picture back. How does that work under the hood, connecting the text to the image generation?
Okay, let's walk through the generative process again, focusing on the text guidance. It starts with text encoding. Your input prompts something like a photorealistic oil painting of a cat wearing a tiny hat sitting on a stack of books, is fed into a powerful pre-trained text encoder, very often CLIP's text encoder, to get a rich numerical embedding that captures the meaning and nuances of the prompt.
Okay, so the text prompt becomes this guiding numerical thought, or vector. Then the diffusion part starts.
Right. Remember the two diffusion processes. During training only, there's the forward diffusion process where real images are gradually noised. The crucial part is the learned reverse denoising process. Here, a neural network, typically a UNet architecture, is trained to predict the noise that was added at each step, given the noisy image and the text embedding of its caption.
So the denoising network sees both the noisy image and the text description during training.
Yes, that's key for conditional generation. Then, for guided generation, creating a new image, you start with pure random noise. At each step of the revision process, the UNet takes the current noisy image and the text embedding of your desired prompt as input. It predicts the noise, but that prediction is influenced or guided by the text embedding,
How does the text embedding influence the noise prediction?
often through cross-attention layers within the UNet architecture. The noisy image representation attends to the text embedding, allowing the model to incorporate semantic information from the prompt into its denoising prediction at each step. This steers the whole process, ensuring that as the model iteratively refines the noisy tensor, it's constantly moving towards an image that matches the specific text description you provided.
That's the part that still feels like intricate magic to me. Turning random noise into a specific, often highly detailed and creative image, all guided by just a sentence.
It is incredibly powerful. And one more key optimization made this feasible on consumer hardware: latent diffusion, which is used by Stable Diffusion.
Latent diffusion, what's that?
Instead of performing this computationally expensive denoising process directly in the high-dimensional pixel space of the image, which can be huge, latent diffusion models first use an autoencoder, specifically a VAE variational autoencoder, to compress the real images into a much smaller, lower-dimensional latent space.
Okay, compress the image first.
Right. Then, the entire diffusion and denoising process, both forward and reverse, guided by text, happens in this compact latent space. This is much, much faster and requires less memory. Once the denoising and latent space is complete, the VAE's decoder is used to transform the final latent representation back into a full-resolution pixel image.
Clever. Do the diffusion in the cheap small space, then upscale at the end.
Exactly. It was a major breakthrough for making high-quality text-to-image generation practical. And this whole process, again, really highlights the modularity we've been talking about. These sophisticated systems are compositions of multiple pre-trained components: vision encoders, text encoders like CLIP, fusion modules like cross-attention, denoisers like UNets, autoencoders like VAEs. Modern AI development is increasingly becoming an exercise in skilled systems integration.
That's a really important point. It's not just one monolithic model. Okay, to truly excel in this field, especially for these advanced tasks, knowing the right data sets for training and benchmarking is crucial. Could you give us a quick rundown of the essential ones here?
Certainly. We've mentioned a few already, but let's recap and add one more giant. For VQA V2, based on Kokio images over 1 million questions. GQA focuses on compositional reasoning, structured questions based on scene graphs. And SLIV, synthetic scenes for pure reasoning tests, for general vision tasks like object detection, segmentation, captioning. CoQ, common objects and context, is a cornerstone benchmark with its rich annotations for over 200,000 images across 80 object categories. And for the massive scale pre-training of models like CLIP and large text-to-image diffusion models. LAI in 5B is absolutely pivotal. It's not perfectly curated, being web-scraped, but its sheer scale, 5.85 billion image text pairs, has been instrumental in training some of the most powerful foundation models we have today. Understanding the scale and nature of these data sets is key to understanding the capabilities and limitations of the models trained on them.
Right, the data really shapes the model. Okay, so we've journeyed through the theory, the architectures, the key models, the data sets. We have all the pieces. But how do we actually turn all this knowledge into a robust, reliable, and scalable product that's ready for the real world?
Yeah.
It's one thing to run a cool demo in a Jupyter notebook,
Oh, yeah.
but it's quite another leap to build a real application that people can depend on.
Exactly. And this is often where the, let's say, academic world meets the engineering reality. What's fascinating and is sometimes daunting is that a production AI application is far, far more than just the trained model file sitting there.
It's a whole system.
It's an entire ecosystem of interconnected components, processes, and infrastructure. This is where true deep expertise really shines. Being able to translate those cutting-edge concepts from a research paper or a notebook into a production-ready system. It means adopting best practices from software engineering and specifically MLOps machine learning operations to ensure your AI application is robust, maintainable, scalable, and can actually stand up to the messy demands of the real world.
MLOs, right. Let's make this concrete. Can we maybe blueprint a real project to see how all these pieces fit together in production?
Absolutely. Let's imagine we're building a multimodal document analysis co-pilot.
A co-pilot for documents. Okay, tell me more. What's the problem it solves?
The problem is clear and common. Analysts, researchers, students, anyone dealing with complex documents often face dense PDFs. Think financial reports, scientific papers, legal contracts. These documents are inherently multimodal. They contain crucial information not just in the running text, but locked away in tables, charts, diagrams, figures.
Right, and manually digging through hundreds of pages to find specific data points or understand a complex chart is incredibly time-consuming and inefficient.
Exactly. So our proposed solution is an AI-powered tool, maybe a web application with a chat interface. A user could interact with it using natural language. They could ask things like, summarize the key findings from the abstract, or what does the bar chart on page 12 show, or extract the data from the main table comparing Q1 and Q2 results, or even describe the methodology illustrated in Figure 3.
Okay, that sounds incredibly useful. How would it work under the hood? What's the system architecture?
The core architecture would likely be a multimodal retrieval augmented generation pipeline, or multimodal RAG.
Rag on, I know that for text. You retrieve relevant text chunks to give context to an LLM. How does it work multimodally?
Good question. A standard text RGAG system retrieves only text chunks. Our multimodal RGAG needs to be smarter. When the user asks a question, the system needs to retrieve not only the most relevant text passages from the document, but also potentially relevant images like charts or figures or tables.
Retrieve both text and visuals based on the query.
Precisely. This combined retrieved context, the relevant text snippets, and perhaps the actual images or structured table data is then packaged together and fed into a powerful multimodal large language model. Think something like GPT-4 with Vision, GPT-4v, or an open-source alternative like Elave. This model then uses all the provided context to generate the final informed answer in natural language.
So the data pipeline that prepares the document for this retrieval is absolutely critical. If the data is the backbone, how do we engineer a really robust pipeline for something like this, especially dealing with these messy PDFs that have text, images, and tables all mixed together?
You've hit the nail on the head. The computer vision data pipeline for pre-processing these documents is foundational. It would typically involve several key steps. Step 1, ingestion and raw extraction. We start by taking the input PDF file. We use a powerful Python library like PyMaPDF or similar. This library can extract not just the raw text, but crucially the text along with its bounding box coordinates on the page.
The coordinates are important.
Absolutely vital. We also need to extract all embedded images, saving them as separate image files like PNG or JPG. And we'd use specialized tools, maybe Camelot Pi or others, to identify and extract tabular data, hopefully preserving its structure.
Okay, got the raw text with locations, the images, the tables. What next?
Step 2, data curation and chunking. Raw extracted text is often messy or too long. We need to clean it up and break it down into smaller, semantically meaningful chunks. A common technique is using something like a recursive character text splitter, which tries to split text along natural boundaries like paragraphs or sentences.
Chunking for retrieval, right?
Exactly. But here's the crucial multimodal part, image caption pairing. Using those bounding box coordinates we extracted, we can try to intelligently associate extracted images with nearby text that is likely to be their caption or a relevant description. This creates explicit links between the visual and textual elements.
It's clever, using the layout information. Okay, so now we have curated text chunks and hopefully linked image caption pairs. What happens to them?
Then comes step 3, multimodal embedding generation. This is where we convert all our curated content into numerical representations or vector embeddings that capture their semantic meaning. The text chunks would be passed through a text embedding model, like a sentence transformer. The extracted images would be passed through a pre-trained vision encoder, maybe CLIP's image encoder. The goal is to get embeddings for both text and images that live in the same or a comparable semantic vector space.
So similar concepts, whether in text or image, end up close together in this vector space.
That's the idea. Finally, step 4, storing in a vector database. All these generated embeddings for text chunks, for images, maybe even for tables, along with their original source content, the actual text, the image file path, and any useful metadata, page number, coordinates, chunk ID, are indexed and stored in a specialized vector database. Examples include open source options like Milvus or ChromaDB or managed cloud services like Pinecone. This database is optimized for incredibly fast vector similarity searches, which forms the core engine of our retrieval system.
Wow, that's a pretty involved pipeline just to prepare the data.
Yeah.
This raises that crucial question again. How do we ensure this whole complex process, from PDF ingestion to vector DB indexing, is repeatable, maintainable, reliable, and continuously improving? This sounds like it needs serious engineering discipline.
It absolutely does, and this is precisely where MLOps principles become essential, applying the rigor and automation of DevOps specifically to the machine learning lifecycle. It's not just about the model, it's about the entire process.
So how would MLOps look for our document copilot pipeline?
Okay, several key practices. First, a standardized project structure. Having a clean, predictable folder layout for data, SRC, source code, tests, configuration files, etc., makes the project understandable and maintainable for everyone on the team. Second, configuration management. No hard-coded values like API keys, model names, database connection strings, or chunking parameters in the code. All of these should be externalized into a configuration file, maybe a config.yaml. This makes it easy to change settings for different environments, development, staging, production, without touching the code.
Good software practice in general.
Totally. Third, dependency management. Using virtual environments, Venv or Conda, and pinning exact package versions in a requirements.txt or environment.aml file is crucial for ensuring that the code runs exactly the same way on every developer's machine and in deployment. Reproducibility is key.
Avoids the works on my machine problem.
Exactly. Fourth, experiment tracking. When we're developing or improving our indexing pipeline, we need to track what worked and what didn't. We'd use a tool like MLflow. We could wrap our indexing script as an MLflow run, logging important parameters like the chunk size strategy, the embedding models used, and output artifacts like metrics about the generated index or even the index itself. This allows us to systematically compare different approaches and reproduce successful results.
So you have a record of every experiment.
Yeah.
What about code quality?
That's where continuous integration CI comes in, usually implemented with tools like GitHub Actions or GitLab CI. Every time a developer pushes code changes, automated checks should run. Code formatters like Black, linters like Flake8 or Rough to catch style issues and potential bugs, and crucially, unit tests written using frameworks like PyTest to verify that individual components of the pipeline still work as expected. CI prevents broken code from being merged into the main branch.
Automated safety net.
Precisely. And when choosing MLOps frameworks to help manage all this, you have options. MLflow is excellent for experiment tracking and model management. Kubeflow is a more comprehensive, heavyweight platform for orchestrating complex ML workflows on Kubernetes, often suited for larger enterprises. And newer frameworks like ZenML aim to provide more abstracted, tool-agnostic way to define and run reproducible ML pipelines across different infrastructures. The key takeaway is that applying these MLOps practices transforms the project from a one-off script into a reliable, maintainable, and evolvable system.
Okay, fantastic. We've built the pipeline, applied MLOps rigor. Finally, we have this amazing document copilot ready. How do we actually get it into the hands of users and, just as importantly, ensure it stays reliable and performs well over the long haul?
We're at the final hurdles: deployment and monitoring. Step 1. Building an inference service. We need to expose our copilot's functionality as an API. A popular choice in Python is using a web framework like FastAPI. We'd create an API endpoint, maybe ask, that takes the user's question in the document ID. This endpoint's logic would load the necessary models, embedding model, multimodal LLM, connect to the vector database, perform the multimodal retrieval step, package the context, call the LLM to generate the answer, and return the response.
So wrap the core logic in a web service.
Exactly. Next, step 2, containerization with Docker. To ensure our application runs consistently everywhere on a developer's laptop, in testing, in production, we package the entire application, including the Python code, all its dependencies from requirements.txt, maybe even model files if they're small enough, into a Docker container.
Yeah.
This creates a standardized, portable unit.
So it's like sealing the entire working application inside a self-contained box. And then how do we run this box and make it available to the world?
Then comes step 3, deployment to the cloud. We push our built Docker image to a container registry, like Docker Hub, AWS, ECR, or Google Artifact Registry. From there, we can deploy it to various cloud services. For simplicity and scalability, managed services like AWS App Runner, Google Cloud Run, or Azure App Service are great options. They take our container image and handle the underlying infrastructure, networking, scaling, automatically adding or removing instances based on traffic, and deployment updates for us. Our Copilot becomes accessible via a public URL.
Okay, it's live. Users are interacting with it. We're done.
Not quite. Deployment is really just the beginning of the operational lifecycle. Step 4. Monitoring and feedback loops are absolutely crucial for long-term success and maintenance.
Monitoring, like, server crashes.
That, yes, but much more. We need structured logging within our Fast API application, logging key information about each request, the question, the document ID, the retrieved context, which text chunks, which images, the final answer generated by the LLM, and the request latency. We also need infrastructure monitoring using cloud provider tools like AWS CloudWatch or Azure Monitor to track CPU memory usage, error rates, and API latency.
Okay, keeping an eye on performance and errors. What about feedback?
A user feedback loop is invaluable. Even something simple, like a thumbs up, thumbs down button next to each answer in the UI. Collecting this feedback tells us which answers were helpful and which weren't. This provides high-quality data that can be used later for fine-tuning the LLM, improving the retrieval strategy, identifying weaknesses in the data pipeline, maybe certain types of charts aren't processed well, or deciding when to re-index the documents.
So feedback helps you improve over time.
Critically, it also helps detect concept drift. The types of documents users upload or the information they seek might change over time. Monitoring performance and feedback helps us identify when the world has drifted away from what the model was initially trained or optimized for, signaling that updates or retraining might be needed. All of this really reinforces that holistic view. A production AI application isn't just a model, it's a continuously monitored and evolving ecosystem of interconnected engineering components.
Wow, okay. We have really charted a comprehensive path today. It feels like we went from the very basics, how machines see individual pixels,
Right, that grid of numbers.
all the way through the revolutionary deep learning architectures like CNNs and ViTs that enabled them to learn complex patterns, then bridging the senses with multimodal AI like CLIP.
Fusing vision and language.
And finally, getting our hands properly dirty with the practical engineering and MLOps required to build and deploy a complex real-world system like our document analysis copilot, from pixels to pipelines, literally.
And this entire journey, this deep dive, really culminates in a crucial understanding, I think. The skills we've discussed today, from grasping the nuances of multimodal perception to mastering data pipelines, embedding strategies, vector databases, and the discipline of MLOps. These are the very foundations required for what many see as the next major frontier in AI agentic systems.
Agentic systems, AI agents.
Exactly. Our research copilot is reactive, it responds to user queries. But imagine an AI agent that can do more, an agent that can proactively perceive its environment, using the multimodal perception we've explored, reason about it, make plans, and actually take actions or use tools to achieve goals. That's where a lot of research and development is heading. And the ability to perceive and understand a complex multimodal world is the necessary sensory input for such an agent to operate effectively, whether in the digital realm or potentially the physical world.
That's a fascinating connection. The skills for building today's systems are the bedrock for tomorrow's agents. So the journey to deep expertise here is definitely continuous, and goodness knows the field moves incredibly fast. For listeners who are inspired now to keep learning, to really build this expertise, what are some invaluable resources you'd recommend?
Great question. Staying current is key. I'd highly recommend following the top academic conferences. These are where the latest breakthroughs are often published first. For computer vision and related areas, keep an eye on CVPR, ICCV, and ECCV. For broader AML, NeuroPS, and ICML are crucial.
Okay, the top conferences. What about more structured learning?
For structured learning, there are some fantastic, high-quality online courses. Andrew Ng's original machine learning course and his deep learning specialization on Coursera are still excellent starting points. Platforms like Udacity offer nanodegrees focused on AI and ML engineering. And I'm a big fan of Fast.ai, which takes a very practical, code-first approach to teaching deep learning.
Good online resources. Should people read the original papers too?
Absolutely. To truly grasp the core ideas, there's no substitute for digging into the foundational papers themselves. Reading the original works on, say, transformers, attention is all you need, key CNNs like AlexNet, VGG, ResNet, GrayNNs, diffusion models, the vision transformer, VIT, and of course CLIP gives you insights you won't get from summaries alone. It can be challenging, but incredibly rewarding.
And finally, getting hands-on.
Definitely. Get hands-on with the tools. The open source libraries and communities are amazing resources. For core vision tasks, OpenCV is indispensable. For deep learning, master either PyTorch or TensorFlow, or both. And the Hugging Face ecosystem is just incredible. They're transformers, diffusers, datasets, and evaluate libraries. Plus, the Model Hub and Active Community have dramatically accelerated development and accessibility in NLP, vision, and multimodal AI. Contributing to or just actively using these libraries is a fantastic way to learn.
That's a wealth of resources, conferences, courses, papers, and open source tools.
This path, building this expertise, is undoubtedly challenging. It requires dedication, but it's also immensely rewarding. And just remember, as we've emphasized today, true, deep expertise in AI now isn't just about understanding algorithms in a theoretical sense or in a notebook. It's really evolved into a multidisciplinary engineering skill set that deeply integrates data engineering, software engineering, and systems thinking alongside the core ML concepts.
That's a perfect summary. Okay, let's leave our listeners with one final provocative thought to mull over, something building on our discussion today. Consider this. How could the principles of multimodal AI and the systems integration skills we discussed today allow an AI agent not just to understand the world through multiple senses, but to actually intervene in it, to take actions based on that understanding? What complex ethical considerations and societal impacts does that possibility raise for the future of AI development? And maybe more personally, how will you, the listener, contribute to shaping that future responsibly as you continue your own learning journey?